Good morning to everyone. Myself T. Muthukumar, Assistant Professor, Pungunadu College of Engineering and Technology. Today, I am going to deliver a lecture on measurement of high DC voltages in high voltage engineering subject. So, why we need to measure high voltages in high voltage engineering? So, in industrial testing and research laboratories, it is essential to measure the voltages and the currents accurately. So, very important to measure the high voltage and current accurately to ensure the perfect safety to the personnel and the equipment. So, we need to protect the equipment as well as handling person, human being from the high voltage. So, this is the very essential or need of the measurement of high voltage. So, ensuring perfect safety to the personnel and equipment. This is the necessity of measuring high voltages and currents. So, hence a person handling a equipment as well as metering devices must be protected against the over voltages and also against any induced voltages. So, human being and also metering device should be protected from the over voltage, so against induced voltage due to stray capacitance coupling. So, therefore, the location and the layout of the devices are important. So, electromagnetic interference is a serious problem in impulse voltage and current measurement, and it has to be avoided or minimized during the measurement. So, from that, we should understand. So, measuring high voltages and high currents is to protect the measuring devices, or protect the equipment, also to protect the human being from the high voltage. So, high voltage measurement techniques. So, in this, a lot of techniques are available to measure the high voltages and currents. So, first, so type of voltage. So, voltage may be classified into DC voltage, AC voltages, and also AC high frequency voltages, impulse voltages, and other rapidly changing voltages. So, in this session, so only we are going to discuss measurement of DC voltages using some measuring devices. So, to measure the DC voltage, so first method is the series resistance micrometers. So, we are going to connect the series resistance with the micrometer to measure the DC voltage. So, second one is resistance potential divider. With the help of potential divider arrangement, we are able to measure the input high voltage. So, third one is generating voltmeter. Fourth one is sphere and other spark gaps. So, these four methodologies are techniques used to measure DC voltages. So, next, the method or techniques of AC voltage in power frequency, series impedance ammeter, potential divider that may be resistance or capacitance type, potential transformers, this electromagnetic type or CVT type. Fourth one is electrostatic voltmeters. Fifth one is sphere gaps. So, third, measurement of high frequency voltage, that is higher than the power frequency, that is called high frequency voltage, impulse voltage, and other rapidly changing voltages. So, this following methodology is to measure these type of voltages. First one is potential dividers with cathode ray oscillators, that is CRO, that may be resistive or capacitive dividers. Peak voltmeters, sphere gaps. So, these three methodology is to measure high frequency voltages, impulse voltages, and other rapidly changing voltages. So, we are going to discuss only so measurement of DC voltages in this lecture session. So, first method is series ohmic resistance with micrometer. So, this is the diagram. So, in this is the high voltage terminal. So, this is the high voltage terminals. So, our aim is to measure this high voltage. So, here we are going to connect so high resistance in series. So high DC voltage are usually measured by connecting a very high resistance, that is the range is few hundreds of mega ohms in series with micrometer. So here R is connected in series with the high voltage terminal in series with the micrometer. So mu A is called micrometer. Here we are going to measure current flowing through the resistor R. So only the current I flowing through the large calibrated resistor R is measured by the moving coil micrometer. So this ammeter is based on the moving coil type. The voltage of the source is given by V equal to IR using the Ohm's law concept. So V equal to IR. So we are going to measure the current I. So we are already known the resistance value. So the product of I and R gives the high voltage values. That is V is equal to IR. The voltage drop in the meter is negligible. So it does not drop any voltage. We are going to assume negligible voltage drop, as the impedance meter is only few ohms compared to, that is impedance of the meter is micrometer is few ohms. It is small compared to the few hundreds of mega ohms, the series connected resistors. So impedance of the micrometer is less compared to the series connected resistors. Here protecting devices, so like a paper gap or neon glow tube or a Zener diode with a suitable series resistance is connected across the meter. So this protecting device is connected across the gap in case of any failure in the series connected resistors or flashover occur in the system. So this high resistance connected in series with the micrometer used to measure current in the resistor, or with the help of resist current value we are calculating the voltage value of the high voltage terminal. V is equal to IR. Here protecting devices used to protect the ammeter from the failure of resistor or flashover. So the resistance is constructed from a large number of wire wound resistors in series. So it is made up of large number of wire wound resistors in series. So limitations of the series resistance design. So there are some limitations. So first one is power dissipation under source loading. So power dissipation may be higher because of using the high resistance. Source loading also possible. So temperature affects and long-term stability. So temperature affects the stability, and also stability issues for the long duration. Voltage dependent of resistive element. So the resistive element dependent on the voltage. So it is one of the drawback. The next one is sensitivity to mechanical stress. So if any mechanical stress applied means, so automatically the performance of the or output voltage of the device will be somewhat deviate. So these are the limitations of the series resistance design. So next, second method is resistance potential dividers for measuring the DC voltage. So here, so we are going to use the potential divider arrangement for measuring the high voltage. We are taking the two resistance in potential divider manner. So one is R1 is the resistance, it is connected in series with the high voltage line. So next one is that is R2. So these two resistors are connected in potential divider arrangement. P is called protecting device. So ESV, that is called electrostatic voltmeter. So we are going to measure the voltage across the resistor R2 with the help of electrostatic voltmeter. So with the help of this voltage divider rule or potential divider concept, so we are able to calculate this high voltage very easily. The influence of temperature and voltage on the elements is eliminated in the voltage divider arrangement. So in previous method, CI series meter method, the temperature will be affect the performance. So in this case, the influence of temperature and the voltage on the elements is eliminated in the voltage divider arrangement. So with the help of this formula, the high voltage magnitude is given by V is equal to R1 plus R2 divided by R2 into V2. So R1 plus R2 divided by R2 into V2. So V2 is the DC voltage across the low voltage arm. Here, that is V2 is the voltage across the R2. So V1 is the voltage across R1. So this voltage is calculated from the potential divider element. So first we are going to calculate voltage across R2 with the help of ESV. With the help of this formula, we are able to calculate the high voltage. With the sudden changes in the voltage, damage may occur to the divider elements. So if any sudden changes in the voltage or damage may occur in the divider element due to the stray capacitance across the element and due to the ground capacitance. So it is possible for the damage of potential divider element due to stray capacitance across the elements and due to the ground capacitance is possible. So to avoid these transient voltages, voltage controlling capacitors are connected across the elements. So we already discussed in this diagram. So capacitor is connected across the elements. This is the series resistor with the parallel capacitance for potential polarization for transient over voltage. To eliminate this transient over voltage, we are connecting the capacitors across the resistance. The potential dividers are made with 0.05% of accuracy up to 100 kV. So if you measure 100 kV voltage, the accuracy is 0.05%. If you want to measure 300 kV, the accuracy is 0.1%. So if you want to measure 500 kV, the accuracy is 0.5%. So 0.5% accuracy for 500 kV. This is suitable for the high voltage measurement. So third method is generating voltmeters. So here we are going to apply the generating concept for measuring the high voltages. So high voltage measuring devices employ generating principle when source loading is propagated or when direct connections to the high voltage source is to be avoided. So if you are not able to directly connect the equipment to the high voltage terminal, and also when the source loading is propagated means, so we are going to employ the generating principle for measuring the high DC voltage. So here a generating voltmeter is a variable capacitor electrostatic voltage generator. So it is works on the principle of variable capacitor concept. So variable capacitor electrostatic voltage generator which generates the current proportional to the applied external voltage. So with the help of this generator, we are going to generate the current proportional to the applied external voltage. From the current value, we are able to calculate the external applied voltage. So the device is driven by an synchronous or constant speed motor and does not absorb power or energy from the voltage measuring source. So electrostatic generating voltmeter so uses the rotating rotor section. So the device is driven by an external synchronous or constant speed motor. So this motor does not absorb any energy or power from the measuring device. So we are using the variable capacitor concept and synchronous motor or constant speed motor to drive the rotor. So this is the constructional diagram of the generating voltmeter. So it has the 4 electrodes. So S1, S2 is called fixed electrodes. So this S1, S2 is called fixed, that is field electrodes. So this is the field winding. So fixed electrodes S1 and S2. So S0 is called two-pole rotor winding, that is armature winding, two-pole rotor winding. So S3 is called high voltage electrode. So we are going to connect the high voltage here, our high voltage terminal in HV electrode. So S3 HV electrode. So S0 is the two-pole armature rotor. S1 and is the field electrodes. So this is another structure. So here motor, that is constant speed motor, a synchronous motor is used to drive the rotor S0. So S1 and S2 is called field electrodes. So with the help of the movement of the motor, so AC EMF will be induced due to the variable capacitance. So this capacitance effect current will be caused. This AC current is rectified by the DC. So with the help of rectifier and diode arrangement, finally, so we are going to measure the current in the micrometer. So S3 is called high voltage terminal. So this is the constructional diagram of generating voltmeter. So operating principle. The charge stored in the capacitor of capacitance. So it works under the principle of variable capacitance concept. So charge in the capacitance C is equal to Q is equal to CV. So charge is equal to C into V. That is capacitance value into potential difference. So if the capacitance of the capacitor varies with the time, when connected to the source voltage V, the current through the capacitor. So capacitor will be variable if the source voltage is applied. So variable current I is equal to dq by dt. So that's equal to V into dc by dt plus C into dv by dt. So I is the formula. So for DC voltages, dv by dt is equal to 0 because rate of change of voltage is 0. So therefore I is equal to dq by dt. That's become V into dc by dt. V into dc by dt. So if the capacitance C varies between the limits C0 to C0 plus Cm sinusoidally. So here capacitance variation will be in sinusoidal manner. So C0 and C0 plus Cm between the limits C0 and C0 plus Cm. So from this again, finally we are going to write capital C is equal to C0 plus Cm into sin omega t. C is equal to C0 plus Cm sin omega t. The current I is, so I is Im cos omega t. So Im, this is the maximum current. Im is equal to Vcm into omega. So Vcm into omega. So Im is the peak value of the current. Therefore, the RMS value of the current is given by IRMS is equal to Vcm omega by root 2. Vcm omega by root 2. So this variable voltmeter, generating voltmeter, so generate the current I. This is proportional to the applied voltage. So IRMS is equal to Vcm omega divided by root 2. So here generating voltmeter with a rotating cylinder consists of, so this is a rotating cylinder, so consists of two excitation field electrodes, that is S2 and S1. So two field electrodes are S1 and S2. And here rotating two-pole rotor, that is two-pole armature driven by a synchronous motor with a constant speed. So driven by a synchronous motor at a constant speed n. So AC current flows between the two hulls of the armature. So AC current flows between the armature of the hulls. So it is rectified by a commutator whose arithmetic mean value may be calculated as. So it is rectified by a commutator whose arithmetic value may be written as I is equal to n divided by 30 into del C into V. So del C is equal to C max minus C minimum. That is the variations in the capacitance C max minus C minimum. So I is equal to n divided by 30 del C into V. For symmetric voltage, C minimum is equal to 0. For symmetric condition, C minimum is equal to 0. So when the voltage is not symmetrical, so one of the electrode is grounded, the C minimum as a fixed electrode. So symmetrical means C minimum 0. Non-symmetrical means one of the electrode is grounded and C minimum has a finite value. The factor of proportionality n divided by 30 into del IC is determined by the calibration. So this is proportional by the calibration. So from this equation, so I is directly proportional to V. So this device can be used for measuring the AC voltages, provided the speed of the drive motor is of the frequency of the voltage to be measured. So we measure the AC voltages. So thus for a 4-pole synchronous motor, if you use the 4-pole synchronous motor with 1500 RPM is suitable for 50 Hz. So we want to measure the 50 Hz AC. We need to use the 4-pole synchronous motor with 1500 RPM. Next. So this is the schematic diagram. So already we discussed. So it consists of two field electrodes, fixed electrodes S1 and S2. So rotating rotor. So this is S3 HV electrode. So generating voltmeter employ rotating sectors or bands for the variation of capacitance. So from S3 to S0, the capacitance will be varied during the rotation of the rotor. The high voltage source is connected to a disk S3. So we are going to connect the high voltage to the disk S3, which is kept at a fixed distance and the axis of the other low voltage electrodes. So it is connected in the same axis, but some different distance between the low voltage electrodes. So S0, S1, S2 are called low voltage electrode. S3 is a high voltage electrodes. The rotor is not driven at a constant speed by a synchronous motor. So by a synchronous motor, S0 is driven by a constant speed at a suitable speed of maybe 1500, 1800, 3000 or 360, 600 RPM. The rotor vans of S0 cause periodic change in the capacitance between the insulated disk S2 and S3. So the variable rotor vans. This is the main reason for the variable capacitance between the S3 and the S0. Sorry, S3 and S2. So capacitance varies in sinusoidal manner. The shape and the number of the vans of S0 and S1 are so designed that they produce the sinusoidal variation in the capacitance. It should produce the sinusoidal variations in the capacitance. So the generated AC current through the resistor R is rectified. So here, so AC current will be generated. This current is rectified through the resistor R by moving coil and read by the moving coil instrument. So the current will be measured by the moving coil instrument. So this instrument is calibrated using potential divider or sphere gap. So this should be calibrated using the potential divider or sphere gap arrangement. Next, advantages of generating voltmeter. So no source loading by the meter. So you are using the only, so no source loading condition and no direct connection to the high voltage electrode. For the purpose only we are using the generator voltmeter. So scale is linear and extension of the range is easy. So scale is linear and extension of the range is easy. A very convenient instrument for electrostatic devices such as Van de Graaff generator and particle apparatus. It is very convenient instrument to measure the generating voltages. So limitations. So they require calibration. So we are using the micrometer need for the calibration. Careful construction is needed. The disturbance in position and mounting of the electrode make the calibration invalid. So it is a complex one. The disturbance in position and mounting of the electrodes make the calibration invalid. So these are the advantages and some limitations of generating voltmeters. So finally, so I'm going to conclude this session. So in this session, we discussed the generation of, there is a measurement of high voltage techniques. So in that DC voltages are there, AC voltage power frequencies are there, AC high frequency voltages and impulse voltages and other rapidly changes voltages are. These are the different types of the AC and DC voltages. So here we discussed DC voltage measurements. So with the help of series resistance micrometer, resistance potential divider, generating voltmeter. So in series resistance with micrometer, so we are going to connect so high resistance in series with the micrometer in the high voltage terminal. So from that, so current flowing through the micrometer is measured, so which is proportional to the input applied voltage. So V is equal to R. So protecting device used to protect the equipment whenever the failure and flashover conditions. So limitations are there. One is the power dissipation and the source loading is the problem. Temperature effects and long time stability is one of the problem. Voltage dependent of the resistive elements, sensitivity to the mechanical stress is available. So to avoid these drawbacks, we are going for the other alternative methods. There is a resistance potential divider. So in the temperature effects is not considerable. So voltage divider rule is used to find out the voltage. So here only we are going to calculate the or measure the lower arm resistance voltage R2. That is V2 voltage is measured with the help of ESP. From the calculation R1 plus R2 divided by R2 into V2, we are able to get the input high voltage. So with the help of 5% accuracy for 500 kV is possible to measure. So generating voltmeter. So whenever the source loading is propagated, so similarly, when direct connection to the high voltage source is to be avoided, or the particular two situations, we are going for the generating principles in measuring the devices, measuring the voltages. So generating voltmeter is a variable capacitor electrostatic voltmeter which generates the current proportional to the input voltage, that is the external applied voltage. So here, so two fixed field electrodes are there. So one rotating rotor is available. So one high voltage electrode is available. If you connect this high voltage to S3, the capacitance will be varied between the S3 and S2. So the capacitance variations will be in the sinusoidal format. So due to this capacitance variation, the current is AC current is induced in the rotors, fixed electrodes. So this current is rectified by the rectifier R and read by the micrometer, so mu A. So we are able to measure the current proportional to the voltage. Here, so constant speed motor or synchronous speed motor used to rotate the S0 electrode. So advantages. So no source loading by the meter, no direct connections to the high voltage electrode. Scale is linear and also it is easily extensible. A very convenient instrument for electrostatic devices such as Van de Graaff generator and partial actuators. Limitations are they require calibration, careful construction is needed, disturbance in positions and mounting of the electrode makes the calibration invalid. Thank you.